The first bombs fell before dawn, and the world woke to a war unlike any it had ever seen. Across Europe, armies moved with terrifying speed, cities smoldered in the aftermath of aerial bombardments, and governments struggled to respond to the chaos. Yet beyond the roar of cannons and the screams of civilians, another battle was quietly raging, a battle of numbers, calculations, and information. Soldiers could storm fortresses and tanks could rumble across borders, but victory increasingly depended on speed, the speed of messages, the speed of calculations, and the speed with which one could outthink the enemy. In 1939, the human mind alone could no longer keep pace with the machinery of modern war. This was a challenge that would force humanity to invent something new, the first electronic computers. From the streets of London to the universities of the United States, mathematicians and engineers recognized a startling truth. The traditional methods of computation, long columns of arithmetic performed by hand, were far too slow to meet the demands of a global conflict. Military planners needed firing tables for artillery, estimates of enemy troop movements, and calculations for bombing trajectories. Cryptographers needed to decode enemy messages in real time, sometimes hours, not days, after they were sent. Entire fleets, armies, and air forces depended on precise, rapid calculations. Delays could mean missed opportunities, lost battles, and tens of thousands of lives. The stakes were nothing less than total victory or defeat. In Britain, the problem took on an almost mythic dimension. The German military had perfected the Enigma machine, an electromechanical device capable of creating virtually unbreakable codes. Every message transmitted could be a clue or a trap. Early attempts to decode these messages manually were painstakingly slow. Teams of clerks, often young women known as computers, would spend hours performing calculations that, by the time they were finished, might already be irrelevant. The pressure was relentless. The Allies needed a faster way to decrypt Enigma, and they needed it urgently. The task was colossal. Every day, thousands of messages poured in from the German Army, Navy, and Air Force. Each one carried critical intelligence, and each one was encrypted with a system that changed daily. Across the Atlantic, the problem was no less urgent. The United States Army faced a different challenge: ballistic calculations for its expanding arsenal. Artillery was more sophisticated than ever, and the firing tables required to aim these massive guns depended on complex equations accounting for wind, humidity, temperature, and the rotation of the Earth. Doing this by hand was not only slow, it was prone to error. A single miscalculation could result in catastrophic consequences on the battlefield. The military realized that human computation alone could not meet the demand. Something more reliable, more precise, and vastly faster had to be invented. Even in quieter laboratories, far from the front lines, the pressure of war was palpable. John A. Tanisoff, a physicist at Iowa State College, had already begun experimenting with electronic methods for solving linear equations, inspired by the limits of mechanical calculators. In England, mathematicians like Alan Turing and his colleagues were racing against time to create machines that could simulate the logic of the human mind but at electronic speed. In Germany, engineers were also advancing computing technology, though often for entirely different purposes. The conflict had transformed the pursuit of science into an urgent, high-stakes race. Whoever could harness speed and logic would gain a decisive edge. By 1940, the scale of the challenge became clear. In Britain, the War Office commissioned a top-secret facility at Bletchley Park, where mathematicians, linguists, and engineers worked day and night to crack the codes that could turn the tide of war. Long before the bomb existed, every message intercepted from German units was like a puzzle with thousands of moving parts. For every one of these, teams of humans would attempt to test each possible key combination, a task so enormous that weeks might pass without a breakthrough. Meanwhile, Hitler's generals assumed their communications were secure, unaware that a shadow war of computation had begun. Across the ocean, American engineers faced similar stakes. The U.S. Army's ballistics research team spent countless hours at Aberdeen Proving Ground, calculating artillery firing tables with mechanical calculators. Each table required hundreds of calculations, each taking hours, each vulnerable to human error. The inefficiency was staggering, and the war could not wait. Every day, military commanders in Europe and the Pacific needed precise information that could determine whether an offensive succeeded or failed. Engineers began to consider radical solutions, machines that could calculate automatically, using electricity instead of hand-cranked gears. The idea of a computer in the modern sense, an electronic device capable of general-purpose calculation, was still in its infancy, but the war created the perfect crucible for innovation. The human cost of slow computation was evident everywhere. In France and Poland, artillery units sometimes overshot targets due to errors in manual calculations. Convoys were ambushed because the timing of attacks could not be predicted accurately. Every miscalculation rippled outward, affecting strategies on land, sea, and air. The urgency was not abstract, it was life and death. This pressure forced a remarkable convergence of minds and technologies. Mathematicians who had once been content with abstract theory were now designing machines that could process hundreds, then thousands, of calculations per second. Engineers who had worked on radios and telegraphs were asked to invent devices that could think, or at least mimic thinking, faster than any human. And yet, the challenge was not purely technical. The secrecy surrounding these projects added layers of complexity. At Bletchley Park, workers could not even discuss their tasks outside the walls. In the United States, engineers labored under strict military oversight, often unaware of the broader scope of the war effort. Mistakes were unforgiving, a single leak could compromise entire operations. Every connection soldered, every tube installed, every calculation programmed had to function flawlessly. The pressure produced innovations of staggering brilliance, but also mistakes, exhaustion, and near miraculous recoveries when failures occurred. By the end of 1941, the first seeds of the electronic computing revolution had taken root. The limitations of human computation were stark, but the potential of machines had become undeniable. Teams in Britain and America had proven that calculation could be automated, that information could be processed faster than ever before, and that technology could be a weapon as potent as any tank or battleship. The stage was set for breakthroughs that would not only influence the outcome of the war but transform human society itself. The urgency of World War II had accelerated the invention of machines that, under different circumstances, might have taken decades to develop. Time, mortality, and global conflict had compressed decades of technological evolution into a few short years. The war had made one thing clear: speed and accuracy were as crucial as courage and strategy. Calculations that once took hours could now be reduced to minutes or seconds, giving commanders an unprecedented advantage. Encrypted messages could be broken before their secrets lost relevance. Firing tables could be generated faster than the enemy could adjust. The first electronic computers were not merely machines, they were instruments of survival, tools that allowed humanity to confront the unimaginable complexity of modern warfare. And in this crucible, brilliant minds would rise to the challenge, creating devices whose influence would extend far beyond the battlefields of Europe and the Pacific, shaping the world for generations to come. The countryside outside Milton Keynes seemed ordinary enough, with rolling fields and quiet villages that bore little hint of the secrets they sheltered. Yet inside Bletchley Park, the sprawling estate that had once been a genteel country house, a revolution of thought and technology was quietly underway. The hum of typewriters, the clatter of adding machines, and the low murmur of voices formed a strange, almost hypnotic rhythm that echoed through corridors brimming with urgency. Here, under the cover of secrecy, mathematicians, linguists, and engineers labored to solve one of the most formidable problems of the war, cracking the German Enigma cipher. It was a problem that would test intellect, patience, and courage in equal measure, and it would demand innovations that seemed almost magical at the time. The Enigma machine itself was deceptively simple in appearance. With its keyboard, rotors, and plugs, it could have passed for an ornate typewriter, but inside, it transformed messages into near impenetrable codes. Each keystroke caused the rotors to shift, scrambling letters in patterns that changed with every message. To anyone attempting to read intercepted transmissions, it was a labyrinth of permutations. The Germans believed the code unbreakable, confident in their machinery, yet Bletchley Park's team knew that ingenuity and technology could turn the cipher into a solvable puzzle. Success depended not only on skill but on speed. Messages that could be decoded hours or even minutes faster could save thousands of lives or change the course of an entire campaign. Alan Turing, a young mathematician whose ideas on computation had been largely theoretical before the war, emerged as a central figure in this effort. With his colleagues, he began to conceptualize a machine that could mimic the logical steps a human would take when attempting to crack Enigma, but do so exponentially faster. The challenge was daunting. The code's complexity meant that manual methods were virtually useless. Even the most brilliant minds could not hope to test every possible combination before the information became irrelevant. Turing's insight was to transform the problem into one of systematic elimination, using a machine to perform repetitive, precise steps at a speed no human could match. This machine would eventually take shape as the bomb, a device that became both symbol and instrument of Bletchley Park's extraordinary effort. Construction of the bomb was itself a feat of engineering. Dozens of rotors, wires, and switches were assembled with meticulous care. Electric motors whirred to life, running through thousands of permutations, checking each against logical constraints that might reveal the correct settings for the Enigma machine. Each rotor turned with mechanical precision, each electrical circuit carried potential breakthroughs, and each failure prompted immediate analysis and adjustment. The room-sized machines were noisy, hot, and unforgiving. One faulty connection could render hours of computation worthless. Yet the staff persisted, driven by the knowledge that every hour of delay could cost lives on the battlefields or allow German submarines to strike unimpeded in the Atlantic. Life at Bletchley Park was an unusual mixture of intellectual rigor and wartime tension. Teams worked in shifts around the clock, often isolated from their families, sometimes sleeping in spare rooms just to remain close to the machines. Mistakes were costly, but the pressure never broke the collaboration that defined the operation. Young women, often trained specifically for these roles, typed messages, performed calculations, and recorded results with astonishing accuracy. The intellectual intensity of the work coexisted with a unique camaraderie. Colleagues relied on each other's insights, intuition, and discipline in equal measure. It was, in many ways, a battlefield of the mind, where success depended on both technology and human perseverance. The impact of the bomb soon became undeniable. Within months of its operation, decrypted messages began to flow with unprecedented speed. Convoys in the Atlantic could be rerouted to avoid U-boat attacks. Air raids could be anticipated, and troop movements could be tracked in near real time. Each victory, however small, reinforced the value of the machines and the team behind them. Hitler's generals continued to assume their communications were secure, oblivious to the fact that a quiet, invisible force was undermining their plans. Bletchley Park, once a stately estate of hedges and gardens, had become one of the most crucial war assets for the Allies, a place where intellect and technology collided to produce results that machines and humans alone could not achieve. The human element remained central, even as machines took on greater computational responsibility. Analysts had to interpret results, detect errors, and refine methods. A successful decryption was not an automatic guarantee of actionable intelligence, it required careful judgment and contextual knowledge. Linguists studied the language, patterns, and habits of the enemy. Mathematicians like Turing worked alongside engineers to adjust the machines, ensuring that every calculation aligned with practical goals. The synergy between human cognition and mechanical speed created a system that amplified both, producing insights that neither could achieve alone. The bomb was revolutionary, but it was effective because it worked in tandem with human ingenuity. Despite the success, the pressure never diminished. German forces occasionally changed Enigma's settings, forcing the teams to start over, testing new permutations and adjusting their methods. Wartime intelligence demanded constant adaptation, improvisation, and vigilance. The staff learned to expect setbacks, to treat failure as a step toward refinement rather than defeat. The psychological strain was immense, any lapse in concentration could nullify hours of work, and the stakes were nothing less than life and death. Yet the staff persevered, motivated not by fame or recognition. Most of their work remained classified for decades, but by a sense of duty and the profound impact of their success on the war effort. By 1943, the cumulative effect of Bletchley Park's breakthroughs began to shape the broader course of the conflict. Convoys of Allied ships moved with greater safety, the timing of air raids improved, and the intelligence derived from decrypted communications allowed the Allies to anticipate and counter German strategies. The bomb had demonstrated the potential of electronic and electromechanical computation in practical, high-stakes applications. What had begun as a desperate experiment to crack codes had evolved into a systematic, replaceable methodology, illustrating the power of combining abstract theory with disciplined engineering and operational rigor. The legacy of Bletchley Park and the bomb extended far beyond the immediate war effort. The work done within its walls laid the foundations for modern computing, demonstrating that complex problems could be approached systematically using machines guided by logical principles. Concepts pioneered here: automation of calculation, systematic elimination of possibilities, and the integration of human oversight with mechanical speed would inform the next generation of computers, including the fully electronic machines that would emerge in America and later around the world. In this quiet English estate, amid hedges, gardens, and stately halls, the future was being written in electric circuits, relays, and the tireless determination of human minds. While Bletchley Park in England was quietly reshaping the battle of intelligence, across the Atlantic, another front of innovation was taking shape, one rooted not in code breaking but in the complex mathematics of warfare. The United States, gearing up for its eventual entry into World War II, faced a pressing challenge: artillery and ballistic calculations were becoming too intricate for human computers to handle efficiently. Each cannon, each gun, each shell required detailed tables to account for wind, elevation, temperature, and countless other variables. A single miscalculation could render an attack ineffective or worse, endanger American soldiers. Traditional methods of calculation, performed laboriously by teams of mathematicians and clerks, were simply too slow. The urgency of modern warfare demanded speed, accuracy, and reliability that human effort alone could not provide. At the heart of this American computational revolution was John Atanasoff, a physicist at Iowa State College, whose work in the late 1930s laid the foundations for electronic computing. Atanesov had grown increasingly frustrated with the limitations of mechanical calculators, which relied on gears and levers to perform arithmetic, often producing errors and operating far too slowly for practical military applications. With his graduate student, Clifford Berry, Atanesov set out to build a machine capable of solving systems of linear equations electronically, a seemingly narrow goal that would nonetheless become groundbreaking. This machine, later known as the Atanesov-Berry computer, ABC, was designed not as a general-purpose computer but as a specialized device for precise, rapid calculations. The ABC's architecture was revolutionary for its time. Unlike earlier mechanical calculators, it used binary arithmetic, representing numbers as sequences of ones and zeros rather than decimal digits. This approach simplified operations and allowed the machine to perform calculations electronically, using vacuum tubes instead of gears. Memory was achieved through capacitors storing electronic charges, a primitive form of the storage devices that modern computers would later refine. The ABC also employed parallel processing, allowing it to tackle multiple components of a calculation simultaneously, a feature that significantly accelerated its operation. While the machine was enormous by today's standards, filling an entire laboratory bench, its principles foreshadowed the general-purpose electronic computers that would emerge during and after the war. The practical implications of the ABC were immediate. Artillery calculations that had taken teams of human computers hours or days could now be executed in minutes. Engineers and mathematicians could test multiple scenarios quickly, adjusting parameters and refining firing tables with unprecedented precision. Although the ABC never saw direct combat use, it remained a prototype and proof of concept. It demonstrated the potential of electronic computation to meet wartime needs. In effect, Atanesov and Berry had created a machine that could think in ways that human mathematicians could not, processing vast amounts of information with speed and reliability. Their work, largely unknown to the public for decades due to secrecy and patent disputes, would later be recognized as a critical stepping stone toward the digital age. Simultaneously, the U.S. military pursued complementary projects. At Aberdeen Proving Ground, engineers and mathematicians struggled with the sheer volume of calculations required to support modern artillery, naval bombardments, and aerial operations. Every shell required a firing table, every table required hundreds of computations, and every computation carried the risk of error. The need for automation was acute, and lessons from early experiments like the ABC informed the design of larger, more versatile machines. American engineers realized that the future of military operations depended on electronic computation, not just for speed but for the ability to process complex, interconnected data that could inform strategy in real time. The urgency of war created an environment that accelerated innovation beyond what might have been possible in peacetime. Engineers worked long hours under strict oversight, often improvising solutions when components failed. Vacuum tubes burned out, wires disconnected, and circuits overloaded, yet each obstacle became an opportunity to refine the design, improve reliability, and enhance performance. Teams learned to approach problems systematically, documenting errors and successes with the precision of both scientists and soldiers. The pace of innovation was relentless, delays could slow the entire war effort, and every breakthrough had the potential to save lives on the battlefield. Unlike Bletchley Park, which focused on secrecy and cryptography, American efforts emphasized general computational power applied to a range of military problems. The ABC was specialized, but its concepts, binary computation, electronic switching, and stored information, were fundamental to later developments. Military planners began to envision machines capable not only of calculating firing tables but also of simulating entire operations, predicting enemy behavior, and optimizing logistics. The war had revealed that information, like firepower, could be decisive. Machines that could handle complex data faster than humans could tip the balance of power, and American engineers were determined to seize that advantage. Yet these innovations were not purely mechanical. Human ingenuity remained at the core. Designing, building, and operating the ABC required collaboration between mathematicians, physicists, and engineers, each bringing specialized expertise to the table. Atanasoff and Berry's work demanded creativity in electronics, a deep understanding of mathematical principles, and practical skill in assembling delicate circuits. Even as machines processed numbers at unprecedented speed, humans guided the logic, interpreted results, and adapted systems to evolving problems. The partnership between mind and machine that had begun in England with Turing and the bomb was now mirrored across the Atlantic, proving that electronic computation was a global phenomenon driven by wartime necessity. By 1943, the seeds planted by Atanasoff and Berry had begun to influence larger projects, particularly the development of the Electronic Numerical Integrator and Computer, or ENIAC. While the ABC was limited in scope, it demonstrated that electronic computation was feasible and efficient, paving the way for machines capable of more general-purpose calculations. Lessons learned in circuit design, memory storage, and electronic reliability informed the engineers who would soon construct ENIAC, the world's first fully functional electronic computer. The vision that had once seemed theoretical, the idea that machines could handle complex calculations faster than any human team, was now within reach, and the war had made it urgent. The broader significance of the ABC and early American efforts extended beyond immediate military applications. These machines showed that electronic computation could tackle problems of previously unimaginable complexity, from ballistics to scientific research. They introduced engineers and mathematicians to concepts binary arithmetic, vacuum tube logic, and electronic memory that would dominate computing for decades. Moreover, the wartime environment fostered a culture of experimentation and bold thinking, where failure was tolerated if it advanced understanding. The crucible of conflict had produced not just machines, but a methodology, a systematic, iterative approach to problem solving that combined human intellect with the speed and reliability of electronics. Ultimately, the ABC and related projects demonstrated a simple but profound truth: the future of computation was electronic, and it would be inseparable from human guidance. While the war would eventually end, the innovations born out of necessity during these years would reshape society. Engineers and scientists had glimpsed a new paradigm, one in which machines could augment human intelligence, solve previously intractable problems, and operate on scales unimaginable before. What had begun as a response to the practical demands of artillery and logistics would become the foundation of the digital revolution, linking wartime ingenuity to peacetime innovation in a continuum of progress that continues to this day. By the time 1943 rolled around, the world of computation had reached a pivotal moment. Across the Atlantic, the United States was preparing to deploy forces on an unprecedented scale, planning amphibious assaults, massive bombing campaigns, and coordinated movements across multiple theaters of war. The logistical and mathematical demands of such operations were staggering. Calculating artillery trajectories, predicting ballistic behavior, and coordinating troop movements required processing massive volumes of data far faster than any team of human computers could manage. It was clear that incremental improvements in mechanical or electromechanical calculators would no longer suffice. What was needed was a machine that could handle vast calculations electronically, with the speed, accuracy, and flexibility demanded by modern warfare. The solution came in the form of the Electronic Numerical Integrator and Computer, or ENIAC, a machine that would not only serve the immediate needs of the military but also herald the dawn of the electronic computing era. The origins of ENIAC lay in the urgent demand for accurate artillery firing tables for the U.S. Army. These tables were essential for guiding heavy artillery and ensuring that every shell landed on target. Traditionally, producing them had been labor-intensive, with hundreds of human computers performing calculations manually. Even mechanical calculators, while faster than pen and paper, were too slow for the sheer volume of computations required. Engineers John Mauchly and J. Presper Eckert recognized that an electronic solution could revolutionize the process. Drawing on prior experiments, including lessons learned from John A. Tanisoff's ABC, they envisioned a machine that could perform thousands of calculations per second, a speed unimaginable with existing methods. ENIAC was conceived as a general-purpose electronic computer, capable not only of solving artillery problems but also of tackling virtually any numerical computation. Construction of ENIAC was a monumental task. The machine occupied a vast hall at the University of Pennsylvania, stretching over 30 meters long and weighing nearly 30 tons. It contained 17,468 vacuum tubes, 7,200 crystal diodes, 1,500 relays, and thousands of resistors and capacitors. The vacuum tubes, critical for switching and amplification, made the machine both incredibly fast and extraordinarily temperamental. Tubes would burn out with startling frequency, requiring constant maintenance. The engineers devised an intricate system to detect failures and replace faulty components quickly, ensuring that ENIAC could operate continuously. Despite its enormous size and complexity, the machine's operation was based on a simple principle: electronic circuits could execute arithmetic operations orders of magnitude faster than any human or mechanical device, provided the instructions were properly programmed. Programming ENIAC, however, was no trivial task. Unlike modern computers with stored program architecture, ENIAC required physical reconfiguration to change tasks. Cables had to be plugged in manually, switches set to specific positions, and operation sequences carefully coordinated. It was a labor-intensive process, demanding precision, patience, and deep understanding of both mathematics and electronics. Teams of operators, many of them women trained in advanced mathematics, worked in shifts around the clock, meticulously preparing the machine for each computation. Despite these challenges, ENIAC's potential was undeniable. Once programmed, it could perform thousands of calculations per second, completing tasks that had previously taken days in a matter of hours or minutes. The impact of ENIAC on wartime operations was profound. With the machine in operation, the Army could produce firing tables with unprecedented speed and accuracy. Artillery units, previously limited by the slow pace of manual computation, now had access to data that could be updated rapidly, allowing them to respond to changing conditions on the battlefield. Bombing trajectories could be calculated with greater precision, reducing collateral damage and increasing mission success rates. ENIAC's ability to handle complex, multidimensional problems allowed military planners to model scenarios that were previously inconceivable, giving the Allies a critical strategic advantage. In many ways, the machine became a silent partner in warfare, its influence felt not in the front lines but in the calculations that determined where shells landed, ships sailed, and troops moved. Beyond its immediate military applications, ENIAC represented a paradigm shift in human understanding of computation. It demonstrated that electronic devices could process information at speeds far exceeding the capabilities of human intellect alone, opening the door to new possibilities in science, engineering, and industry. Researchers began to realize that problems once considered intractable, complex simulations of physical systems, large-scale statistical analyses, and even early explorations of artificial intelligence could now be approached with electronic computation. ENIAC's success validated the ideas pioneered by Turing in England and Atanasoff in the United States, confirming that the combination of electronic speed and systematic logic could transform not only wartime operations but human knowledge itself. The machine also highlighted the importance of collaboration between disciplines. Building ENIAC required mathematicians, engineers, physicists, and technicians to work in close coordination, each bringing expertise that the others lacked. This interdisciplinary approach proved essential. Electronic circuits had to be designed to handle mathematical operations accurately, while operators had to understand the underlying calculations to configure the machine correctly. Wartime urgency accelerated innovation, pushing teams to develop solutions that might have taken decades in peacetime. The collaborative model established during ENIAC's development would become a hallmark of later computing projects, emphasizing the integration of human insight and technological capability. By the time World War II ended, ENIAC had already proven its worth. It had completed thousands of calculations critical to the Allied war effort, reducing manual labor and enhancing strategic planning. Yet the machine's true legacy extended far beyond artillery tables. ENIAC inspired a generation of engineers and scientists to envision computers as general-purpose tools, capable of solving problems in physics, engineering, finance, and beyond. The concept of electronic, programmable computation, once confined to laboratories and military applications, began to take root in broader society. ENIAC's success demonstrated that human ingenuity, when paired with electronic speed, could overcome challenges previously thought insurmountable, a lesson born in the crucible of war that would shape the technological future for decades to come. The broader significance of ENIAC lies in its demonstration of possibility. It showed that complex calculations, once slow and error-prone, could be automated, accelerated, and scaled. This not only transformed military operations but also set the stage for the post-war computing revolution. Universities, research laboratories, and eventually commercial enterprises began to explore how electronic computation could be applied to science, engineering, and industry. ENIAC's architecture influenced the design of subsequent machines, introducing concepts such as high-speed arithmetic, parallel processing, and the integration of human operators into electronic workflows. The machine became both a symbol and a tool, a testament to human creativity, determination, and the transformative power of technology. In retrospect, ENIAC represents a turning point not just in computing but in human history. The pressures of World War II had accelerated the invention of machines capable of performing tasks far beyond the reach of unaided human thought. ENIAC, building on the ideas of Turing, Atanasoff, and others, transformed computation from a labor-intensive, manual process into an electronic, programmable, high-speed operation. Its creation demonstrated that machines could extend human capabilities in profound ways, solving problems that had once seemed insurmountable. The lessons learned in constructing, operating, and applying ENIAC resonated far beyond the war, laying the foundation for the digital age and reshaping how humanity approached complex, data-driven challenges. The war may have ended, but the legacy of ENIAC and the early electronic computers it inspired was just beginning. The machine proved that speed, precision, and automation could redefine what was possible. It connected mathematics, engineering, and human insight in ways that would become the backbone of modern technology. In the quiet halls of the University of Pennsylvania, amid the hum of vacuum tubes and the careful attention of its operators, a new era had begun, an era in which machines would not only compute but empower humanity to explore problems of unprecedented complexity, forever changing the trajectory of science, industry, and society.